Welcome back, mathematicians. Today's lesson is on making inferences about populations. So what you've been doing so far is working a lot with data, figuring out what kind of sample to use to get the data, but really you haven't gone over what the point is or what the purpose is for collecting that data. And that data is used to make inferences about populations, and that's what we're going over in this lesson. So you're using a random sample to represent that population. And we use this a lot when we compare two or more populations together. We talk about like who has the highest average score between two different basketball teams, three different basketball teams, these kind of things. It's a very kind of basic statistic. Okay, so we can use that information from the basketball teams to make an inference about that team, saying in the future their average score is going to be better than the other two. So that's kind of how we make inferences on populations. We're going to go over some different ways to make inferences, some mean absolute deviation between the populations, and do some comparisons to practice making those inferences, or you could also say it's kind of like a projection or an estimation. And so let's zoom into this first example. So a population consists of test scores of 60 students. So that's the whole population is 60. A random sample of 10 scores has been collected from the population, and then it lists out those 10 scores. So we're going to calculate the sample mean and use it to approximate the population mean. Okay, so again, we're taking a random sample. They're not telling us how they collected that sample, but as long as they say random sample, we can assume that it'll be a good approximation. And we're going to calculate the average or the mean. So because we're not doing the median, remember median is the middle, we don't have to order them from least to greatest. So all we're going to do is we're going to add these numbers together. Okay, so here are our numbers here. And we're just finding the mean of those numbers. So that's 18 plus 10 plus 6 plus 9. And you just keep going. And it says that there are 10 scores, so let's make sure we have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. We divide that by 10. When I add all of these numbers together, I get 114 over 10, and that means that the average is 11.4. Next, we're asked to calculate the mean absolute deviation. So if you recall, that's when we are taking the difference between the average, the mean, and the actual score. So we're going to set up that table again. So we could say that that's score. And then our average. And then the difference. And our numbers are 18, 10, 6, 9, 10, 14, 17, 10, 9, and 11. And the average that I found is this one here. So it's 11.4 for all of them. If you want to do this, you can. And just say that it goes all the way down. That's pretty common for statistics. And now we're going to take the difference. So we're doing the larger number subtracting the smaller number. Or you can just always do subtraction, but make sure that because it's distance from the absolute, so because it's distance from the mean, and distance is always positive, you're just always taking that positive number. So we're just going to go through each of these and find the difference between those scores. So 18 minus 11.4, 6.6. And then we keep going. 1.4, 5.4, 2.4, 1.4, 2.6, 5.6, 1.4, 2.4, and then 0.4. And now if you remember, we have to take all of these and find the average again. So we're adding all of those numbers up. And we're dividing by 10. And so when I add all of those numbers up, and you can use the calculator, and you'll get 29.6 divided by 10, which is 2.96. So the mean absolute deviation equals 2.96. And next we're asked to draw a dot plot for the scores of the mean. So a dot plot is, if you remember, and I think you went through this in 6th grade, but if you don't, we'll go over it quickly now. It's just a number line, okay, starting from your lowest score and then going to your largest score. So our lowest score was 6, and we want to go all the way up to 18. And it's just a number line, so 6, 7, 8. Okay, and since it's a dot plot, what we're really doing is just taking these values. So we have 18 here, okay, and we're putting a dot on 18, and we have 10, so we're putting a dot on 10. And if you have repeats, look how many 10s we have. So that means 10 is going to have 3 dots. And you want to make sure that those dots are pretty evenly spaced out. And that's all there is to making a dot plot. It kind of just shows where most of the data lies. So it's just another way to represent data. And then we'll just keep going with this one. So we have a 6, 9, 14, 17, another 9, and 111. And then what we're going to do is we're going to say, well, the mean, the average was 11.4. So that would be in our number line just about here, kind of a little less than halfway in between 11 and 12. So let's go back and look at our, zoom into our dot plot here. You can tell, and it makes sense because our mean absolute deviation was 2.96. You can tell that all of the, not all of them, but most of the data is really close to the mean. right? Because that absolute deviation was pretty small. And there's another way we can, or another statistic that we can use to calculate or show that the absolute deviation is pretty small, and that's called the mad to mean ratio. I'm just going to highlight that here. It's kind of fun to say, mad to mean ratio. And the mad to mean ratio is just when you take the mean average deviation and you divide that by your mean. So when we do that to this value, we're doing 2.96 divided by 11.4. And when we do that, we get about 0.26. And then as a percent, right, as a percent, we just take that decimal place, so we move it over 2. So it's 26%. And 26% is a relatively low ratio, which means that the scores don't vary that much. So when we're asked to say, using the mad to mean ratio and the dot plot, describe informally how varied the scores are, the answer to that, what we would say is, because the ratio is so small, and we're going to say there are several outliers. So that means if we look at our dot plot, we take a look at 18, 17, 6, right? If we didn't have those numbers there, it would be even closer to the middle because we'd only be looking at this data, right? So we do have some outliers, but at the end, we can say that the data is pretty well spread out. Even with those ratios. I mean, even with those outliers. In the next example, we're comparing the weights of two different teams, two different football teams, using their box plots. So part A asks us to show that the two teams have the same measure of variation. So what they're talking about here is that the difference between the quartiles and that they have the same interquartile range. So what they want to know is, is this range the same? Is this range the same? And then is this range the same? Okay, so we're going to actually calculate that out. So we're going to separate this. We can say team A and then team B. And the first one we're going to do is just quartile 2 minus quartile 1 for team A. And remember, quartile 2 is the one in the middle, right? So for this one, it's 240 minus, and then quartile 1 is 230, which gives you 10. And then we're going to test team B. So that's 230 for quartile 2 minus quartile 1 is 220, which also gives you 10. So those are equal. And let's check the difference between quartile 3 and quartile 2. So for team A, that's going to be 250 minus 240, which equals 10. And then for team B, it's 240 minus 230, which is also 10. So those are equal. Now, what's interesting is that if these two are both equal, then the interquartile range is going to be equal. Because when you think about it, this was 10 for both, right? And then this was also 10 for both. So that means that for both of the interquartile range, it's going to be a combination of each of these measures of variation. So 20 and 20. So we can say that they are the same. Next question is express the difference in median weight in terms of the interquartile range. Okay, so the interquartile range for both are 20. Right, so each of them have an interquartile range of 20. And then their medians, which are these numbers here, right? This range and this range, and this one and this one, those are both 10. So we can say that the difference in their medians. So when we want to answer this one with a sentence, we would say the difference in median weight between the two teams is half the interquartile range. Now, part C says, what inference can you draw about the weight distributions of the players of the two teams? So there's going to be a lot of variations in answers here, but let's go back and take a look at the data. And let me just do a little bit of erasing. So when we're comparing, it looks like when we just look at the range, take a look at this and this, right? Those are the same statistics, right? They're each equal to 10. They're each worth 10, okay? But when we talk about interquartile range, that's also kind of 50% of the data, okay? So that's the same kind of like type of people that we're measuring. So they are similar people between team A and team B. And you can see that here too, right? This is going to be 50% of team A and 50% of team B. So in general, when we look at these two teams, team A is going to be heavier. So that's like an inference that we can say, okay? So that's what I would write down. And then it could be different answers and different inferences that you see. But I would say that because the difference in medians and interquartile range is about 50%, team A is going to be heavier. So in general, team A is heavier. Okay, because as you kind of look at it, and let me just do some more erasing so you can look at this kind of again, the fresh start. If we just take a look at the whole thing here, team B, they almost look like the same thing, team B and team A, but team A is just kind of shifted 10 more to the right. So it's almost like everything is 10 pounds heavier for team A. Okay, so that's like another inference that you could say based on the population. So your answers for this are going to vary. If you check your answers in the book, it'll say that your answers might be around this inference. But a lot of times when people look at data, there's not just one correct answer. People look at data and they see different things. Depends on what they're looking for, what stands out to them. So there are a lot of different answers that can be found. For me, the one that most makes sense is that team A is heavier, and it's because the interquartile range and the like between them, the 50% of each one is about um, 10 more pounds. So for this example, um, we are given a class of students that completed 2 science tests. The scores are presented in the box plots, and we're going to find the median and the range of each of those. So again, we can kind of set up categories: test 1, test 2. And so the median, and remember that's quartile 2, that's the one right in the middle, for test 1 is 50. And the median for test 2 is 55. And the range is when you take the largest number. So for test 1, that's 95. And you subtract the smallest number. For test 1, that's 5. So 95 minus 5, which is 90. And we do the same thing for test 2. It's 90 minus 10. And next we're asked which test has a wider spread of data. So we talk about spread, we're usually talking about range. Because test 1 had a larger range, then test 1 would have a larger spread of data. Okay, whereas test 2 was more narrow, the range was only 80, so it's not spread out as much. In part C, we're asked, on which test did the class perform better? And if we just take a look at the data again, and I'll erase it so we can see it better. So for test 1, okay, about half the data is between 35 and 65. And then for test 2, about half the data is between 45 and 70. Okay, so when you're asked on which test did the class perform better, that's exactly what you would want to write down. And I just kind of paused the video and typed it out for you, or wrote it out for you. So on test 1, 50% of the scores are between 35 and 65. And then on test 2, when we looked, 50% of the scores are between 45 and 70. So the class performed better on test 2, right? And if we just take a look at the data, you can see that everything on test 2, okay, the scores are kind of shifted to the right when we look at just the middle, when we talk about the medians. So even though the range was greater in this one for test 1, right? Test 1 had a higher score than the student in test 2. Well, let's assume that it's the same student. Okay, we'll assume that it's the same student. They may have done better on test 1 than they did on test 2, right? Better here than they did here. But as a class, okay, most of the data, right, and then 50% of the data is in this box plot here, right? 50% of the data is in here. Most of the class did better on test 2. Okay, so it's not just the range you want to look at, it's where most of the data is, and most of the data is inside the box plot. This last example here is a bit of a long one as far as calculating goes. So you're probably going to see me pause the video and write a bunch of stuff down and then talk about it, just because there's a lot of calculations going on, and I'm not going to keep the screen recording going as I just write a bunch of numbers. So here we have a table that shows the game scores for Mark and Jason. And we're asked to find the mean scores for both Mark and Jason. So what I would do is kind of separate them. So Mark on one side and then Jason on the other. And again, when I find the mean, I'm just adding those numbers together and dividing by the amount of numbers we have. So for Mark, that's 2 plus 3 plus 8 plus 5 plus 3 plus 4 plus 4 plus 6 plus 5 plus 4. And let's say I should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm adding those up and dividing by 10. So 44 divided by 10. So the mean for Mark is 4.4. And I'm going to do the same thing for Jason, but I'm not going to record me doing the numbers, which means you can just pause the recording and then you can do Jason's mean yourself. And now that you've done that, you can see that their mean for both are actually equal. So they both have the same average game score of 4.4. And now we're asked to find the mean absolute deviation for Mark and Jason's scores. So this one, and you can take a look back at the previous examples. Remember, mean absolute deviation is where there's a lot of numbers in the table that you're doing. So I'm going to help you set up the table and then going to pause the video and then going to do all the math out. And you can do the same thing now that you've done several of these tables. And hopefully we both come up with the same table and the same mean absolute deviation for each of them. So in this case, we need a table for Mark and we need a table for Jason. So let's say Mark will have his score, and then we'll have his average, and then we'll have the difference. And then Jason will have the same table with score, average, and difference. And so we're just going to list out all those scores that we had and that were given from the table. So 2, 3, 8, and this is marked, so 2, 3, 8, 5, 3, 4, 4, 6, 5, and 4. Right? The average for Mark and Jason both were, sorry, not 11.4, 4.4. And that was all the way through. And then the difference that we would do is we would take the larger number, subtract the smaller number, and we'd get, for this one, 2.4. And then you're doing the same thing for Jason. Okay, Jason started with a 9, a 5, and then the difference for Jason was also, or sorry, the average for Jason was also 4.4. And so that first one I can give you is 4.6 for a difference. Okay, so pause the video now and you complete the tables, and then we'll compare our tables together. All right, so we've both finished our table, and we're trying to calculate the mean absolute deviation for both. So when I add up all of these numbers, okay, I got 12.8. And then to find that average, I divide by 10. So 1.28 would be Mark's mean average deviation. And then the same thing for Jason. I added all of those up, and I got 30 divided by 10. And again, I'm dividing by 10 because there were 10 numbers, and I get 3. So for Jason, it's 3, and for Mark, it's 1.28. So you can see that for Mark, the absolute deviation is significantly lower than Jason's. And that's going to mean that his numbers, right, are closer together. And we'll see that next when we have to draw a dot plot for the data. All right, for this one, right, again, we're going to draw dot plots for Mark and for Jason. And remember, dot plots are just a number line. So we start with the smallest number and go to the largest. For this one, because we're comparing the two, we actually want to do almost kind of have the same number line that we're looking at. So let's just go from 1 to 10 for both Mark and for Jason. It's almost like you don't want to have two different scales when you're graphing, because then when you compare things, since your scales are off, it's harder to compare them, right? Because you're not looking at the data the same way. So we're going to go just from 1 to 10 on both of these number lines. Okay, and so we have the same number line here. One thing I didn't do before, we have a number line, I didn't put arrows at the ends. You do want to do that because you want to show that the number line never stops. So that's just bad form on my part. So make sure you go back and put those arrows in. So both data sets had a mean of 4.4. So we can write those in. And now we're doing is for the dot plots, we're just putting a dot on the scores. So for Mark, he had a 2, and then he had a 3, and I'm just looking at his scores here. So 8, 5, and remember, we want to go kind of keep things level. So everything that has like one dot is kind of the same height above that dot plot there. So we have 3 again, a 4, another 4, 6, another 5, and another 4. So it goes 1, 2 dots, 3 dots, 2 dots, 1 dot, and then another dot on 8. And then we go and we do Jason's dot plot. So his scores were 9, 5, 1. And so remember, I'm keeping all those dots, those 1 dots, the same height above that line. So we had 9, 5, 1, another 1, 2, 8, another 9, 2, and 1, and a 6. So another way to do it is to also count how many dots you have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 dots for Jason, and we have 10 scores. So those numbers look to be just about right. So this next question is compare Mark and Jason's statistics, then compare their dot plots. So I just kind of didn't want you to see the answer, so I made this here. I'm just going to delete that box. So when you look at the statistics, they both have the same mean score, right? They both have a 4.4, but Jason's, right, they both have 4.4 here. Jason's mean absolute deviation was over 2 times as large as Mark's. Okay, so you can see that by the dot plot that Mark's scores are much closer together, okay, whereas Jason's are really farther apart. Okay, so he had a lot of highs and a lot of lows, right? A lot of highs and a lot of lows that led to um, them having the same mean score. Okay, but um, Mark had more centralized scores around his mean. And then the next one, again, I have the blue box. I'm just going to delete that here. What conclusion can you make about the two players' performance in the game? So, what I would say is just kind of when we look at um, their dot plots and we think about their mean absolute deviation. So, Mark's performance is probably more consistent, right? So, he always averages around a 4.4. And then Jason has some highs and some lows. So, his average is still the same. So, if I'm kind of um, let's say looking at which partner I want to use or which team, um, um, which player I want to put on my team. Do I want a more consistent person like Mark, who's always going to get around a 4.4, or do I want a person like Jason who might have some really great games and get an 8 and a 9, or might have some really low games and get a 1 or a 2? So you know. Um, People that look at stuff like this, or things like the NFL draft, whenever you're drafting players, recruiting players for colleges, things like that, where you're looking at the consistency and you're going to see, how often do they deviate from their average, kind of shows how consistent the player is, and whether or not you would want them to be on your team. Lastly, you're just going to be doing these two practice problems on your own. You may have to put them on two different pages. I just kind of squeeze them on one page here, but they're just like the examples we were doing. Okay, so number one is like the first example, and then number three is like the third example that we did. Okay, so in number 3, so we skipped number 2, but in number 3, you're just comparing the two classes. And number 1, you're taking that random sample and then making inferences about the population. And when you're done with these, have them checked by your teacher, and you can move on to the practice problems.